Welcome back. We've now seen lots of different ways for calculating the concentrations of different species in a chemical reaction at equilibrium by plugging things in to an ice table, plugging them into our K expression, and there was different ways of solving. If we were lucky, we could just solve it, or we could square root both sides. If we were a little less lucky, we had to use the quadratic formula. If we were even less lucky, we had to use the small x assumption, and in the worst case scenario, we used the small x assumption followed by the method of successive approximations in order to solve these equilibrium problems. So now we're just going to kind of step back and do stuff that's a little lighter, and we're going to talk about how does K change if we change an equation. So we've got this reaction 2SO2 plus O2 goes to 2SO3, and we can write our K expression for that. K, KQ, KC is going to be the concentration of SO3 squared over the concentration of SO2 squared times the concentration of O2. Right, and that's our K expression. We can calculate it. It's constant. That's the lovely thing about it. What would happen if I doubled that reaction? So I'm going to take it and I'm going to double everything, and I get 4SO2 plus 2O2 goes to 4SO3. Well, I need to write a K expression for that one, so let me go ahead and do it. And I get K is equal to SO3 to the fourth times SO2 squared times, oops, not squared, to the fourth times O2 squared. That's not the same K. It's certainly not the same K value, right? Let's call this K1 and this one K2. Right, the 1 and 2 just referring to my reaction number 1 here and my reaction number 2 here. Chemists love putting subscripts after letters. We do it all the time, and that just helps us identify what we're talking about. Okay, so how are K1 and K2 related? And the answer is they're certainly not equal, right? They're certainly not equal because one has a square on the top and one has a quartic on the top to the fourth power. So how are they equal? Well, it turns out if you look at it, K1 and K2 are related, that if you just take K1 and you square it, you'll get K2, right? If I square SO3 squared, I should get SO3 to the fourth. If I square SO2 squared, I should get SO2 to the fourth. And if I square O2, I get O2 squared, and that's my K2 value. So when I doubled my reaction, what did I do? I squared my K. What do you think would happen if I tripled the reaction? If I said, hey, I've got, now instead of 2 SO2s, I've got 6 SO2s plus 3 O2s goes to 6 SO3. Well, I'd find that K3 of this reaction and would be related to K1. Notice I changed the order of things a little bit by cubing it. My new K is my old K by cubing it. And it turns out this is a generic thing. If you multiply a reaction by n, and so in my example, my n was 2 for the first example, my n was 3 for the first example. And you have to multiply everything, right? You can't just multiply one thing, and it wouldn't be a balanced reaction anymore. But if I multiply a reaction by n, then K, the new K, is the old K raised to the power of n. So when I doubled my reaction, I had to square my K. When I tripled my reaction, I had to cube my K. And it works for any number, not just integers. If I multiplied by a half, then I would take the square root of my old K to get my new K. If I multiplied by -1, right? What is multiplying by -1? That's reversing a reaction, right? Because you can't have negative coefficients on reactions, but it is. It's essentially reversing the reaction. So when I multiply by -1, I get K to the -1. And if you remember way back many videos ago, one of the first questions we said is, oh, we've got this K value. What happens for K with the reversed reaction? And we said it was just 1 over our initial K. Well, that's what K to the -1 is. So this is a general rule, applies for any value of K, including non-integer values and negative values. Okay? So that's a good one to know and be familiar with in case we're trying to manipulate some reactions here. What about if we add reactions? So here we've got a reaction CO plus H2. We've got another reaction CH4 plus H2S. And we're going to add those together. We're going to cancel out anything that cancels when we add them together. You'll notice that CH4 is going to cancel out there. Our K1, if we look at it, is going to be the concentration of CH4 times the concentration of H2O over the concentration of CO times the concentration of H2 cubed. Our K2 is the concentration of CS2, concentration of H2 to the fourth over concentration of CH4 times the concentration of H2S squared. And when I add those up and cancel out, what do I get? I get a K of concentration of CS2, concentration of H2O, concentration of H2 over the concentration of CO, concentration of H2S squared. And you might be looking at those three different K values and being like, I don't see a whole lot of relationship between those three different K values. They look kind of all very different to me. But let's check it out. We know CH4 dropped out, right? So somewhere this guy dropped out and this guy dropped out in our final expression when we added those ones. But H2O, right, appears in the numerator here as a single order. It appears in the numerator here as a single order. That's great. And if we look, H2 appears. Oh, silly me. I'm like, where'd my H2 go? I know where my H2 went. Right. Most of my H2s canceled, right? I had 3 H2s that got canceled here, leaving me with 1 H2 in my final reaction when I added them up. But, right, we've got an H2 to the cube here, an H2 to the fourth up here, and only an H2 here. So I'm going to kind of make a long story short. What I found is that K3 is actually K1 times K2. So when you add reactions, you can actually manipulate their Ks and find out that they are multiplied of each other. So since I added reaction 1 to reaction 2, the reaction 3 has a K of K1 times K2. If I had to add reaction 1 to 2 times reaction 2, I'd get a K of K1 times K2 squared, right? Because I just added 2 of reaction 2s. Or you could say it was K1 times K2 since I added K2 a second time, which would get you the same answer. So those are two important things to know. When I change a single equation by multiplying it by something, I raise K to that power. When I add equations, I multiply their Ks, and again, it works whether it's 2 equations, 3 equations, 4 equations, I just multiply all the Ks. If I combine them, then I just have to make sure to do both steps, right? If I multiply by a reaction and combine a reaction, I have to do that. All right, so here's your chance. I want to know what is the equilibrium constant K for this reaction if the original reaction was this and had an equilibrium constant of K. So this K prime is a notation often used. It's just to say kind of a new one, a changed one. So I want to know what the new K is compared to the old K. Go for it. All right, what did you come up with? Hopefully you said, well, what did I do from this reaction to this reaction? I went from the original reaction on the bottom to the new reaction on the top. I multiplied by 1/2. And if you look through, that's kind of what I did in everything. So if I multiply by 1/2, my new K should be my old K raised to the power of 1/2. Okay? If you got this one down here, it just means you were thinking about it slightly backwards. You had the right idea, but you were trying to go down, like I multiplied by 2 to get that second one. But my original one was the bottom one, so you just have to be careful, right? Whole wording of problems and things like that. And I went to the other one and I got 1/2 of that, so I raised my K to the 1/2. And we don't use this often, but we do use it occasionally, and you will have a chance to use it in the homework a few times for certain, and maybe even on a test. All right, thanks for listening. Bye.